And welcome back, everybody. So in this video, I will talk about the convolution, which is essentially an extension of the superposition principle that I described in the last lecture. So if you remember from our last lecture, we had this equation here, which is the superposition integral, where we have a function of space, right, and we integrate it over. So again, we can have multiple barrels, distributed in space. So this is for a 1D, but obviously in a real case that would be in 2 and 3Ds. And then we can sum over them, right? Just literally sum the individual solutions so that we have the solution for the entire domain. Okay. If we look at what this is, it's really a convolution integral. So we can simply take the basic solution for a pulse, and again, I'm sort of repeating the same concepts here, but if we have a pulse, an initial pulse solution, so if we know the solution for this, which we do know, that's our Gaussian fundamental solution, then we can actually integrate it away by convolving it with any sort of initial condition, right? So if we know the solution for a pulse, we can convolve that pulse with any sort of, initial condition in space and or in time, and then convolve both distributions, so the Gaussian solution for the pulse and the distribution for the initial condition, and find a solution. For example, so again, doing the same example as before, so these were the 3 barrels that we had in that previous lecture on superposition. Here I left the pulses at 600 and 1000, so just flashing the code here if you wanted to pause the video and look back at this code here. But going back to our situation, we can recalculate the solution with the convolution operation, and again, of course, in MATLAB, instead of summing them manually, we can just use a function. There's a function that's coded in MATLAB that is called the conv function. So if we convolve D, which is our initial initial distribution, initial condition, so we have pulses of mass 150 at 0, what was it? 100, 250, I believe, 600 and 1000, right? So now we have an initial condition that is M at those places. We can convolve, we can convolve this initial condition with our pulse solution, right? So we're convolving those two things together and find that the blue solution, so the blue line, right, the result of the convolution here, the blue line and the red dashed line, which is the result of the sum that we did before, right, the superposition principle, is exactly the same. Okay, so this is just to demonstrate that superposition and convolution are the same. Now this is really useful because it's actually true in space and in time. So here's an example that is typically useful for aquifer tests or transport, which are what we call constant source solutions, meaning essentially what you're doing here is you're pumping, you're doing a tracer test, so you're pumping, say, a salt, for example, in a piezometer because you would like to measure the dispersion coefficient of your aquifer, right? So if you want to know what the dispersion is, what you would do is a pumping test or a salt injection in your aquifer. So you would pump some salt into a piezometer and measure it over time in a different piezometer. So again, this is a case where you would now have a conductivity meter, inside a piezometer somewhere else, and then you would measure that salt that salt front come through your piezometer and go by your piezometer as you're pumping salt in that other one. And what the data looks like is this, right? Data typically looks like these, right? So this is a breakthrough curve. Again, this is concentration over time now. So this is a breakthrough curve, and that's not for a pulse, but that's for a pump injection, right? So that's for a steady injection. So you can see how now it goes steady. Remember that error function solution. And then when you stop pumping, obviously now it goes back down, right? And to 0. So this sort of data is pretty typical. What it is essentially is the convolution of a whole bunch of little pulses, right? So if you think of your pump putting salt into your piezometer, what it does is putting a little pulse, right, every second or every, increment of time. So it's a bunch of little pulses that you can then sum together to find your plateau solution. This is a plateau here, right? So this breakthrough curve, again, for a continuous injection or for a pump injection, right, is really the convolution of a whole bunch of little pulses together in time. Okay, so again, the convolution operation really useful to if you have a distribution of initial condition or a distribution of mass as your initial condition, or if you have a distribution in time, right, of mass. So if you have a boundary, which here is time, that changes over time. Again, if you know the pulse solution, you can convolve this with your time, change in concentration and find a solution for your problem. So again, very powerful operation, the superposition / convolution. Okay, I'll leave it here for this topic. And in the next video, we will talk about the moment method to find characteristics of transport. Thank you.